Hello everyone, welcome to Analog Electronic Circuits, lecture number 15, part number 1. Today we are going to analyze a common source RC coupled cascade amplifier, right? So in cascade amplifiers, we take two single stage amplifiers and we connect them in series. And we are using RC coupled because the first stage is connected to the second stage via this RC coupling, right? So in our case, let me just draw and show it to you. So this is my capacitor, and internally this will be the resistors along with R pi, which will make the RC coupling. So this capacitor and the internal resistance, I mean the input impedance of the second stage will become my RC coupling, right? So this capacitor is the link which is connecting the first stage to the second stage. We are using over here the enhancement type MOSFET, N channel MOSFET, and let us decide which is the source, which is the first stage, second stage, and the load. So over here, let me use a different color. So this will become my, let me increase the font size. So this over here is my source, input source. So let me call it as source. Then this over here, excluding the capacitor, this is my load, which is the resistive load in this case. So I'm writing over here load, and in between we have the amplifier. Now in case of an amplifier, we have a first stage. So from here to here is my first stage. So I'll writing over here, this will become the first stage, and this is the second stage. Okay. So the output of the first stage is connected to the coupling capacitor CC2, and which is going to the input to the second stage, right? And so we have also marked, it's very important to mark the gate, drain, and source terminal of the corresponding MOSFET. So individually, single stage amplifier, it's a common source amplifier. And with cascading, it's called as a common source RC coupled cascade amplifier. Now, what is the aim of this analysis? So we are doing this analysis to estimate the input impedance, or it is also called as resistance, right? So whenever we call it resistance, so we can call it as or resistance, we can denote it by Rin. Okay. So we can also call it to estimate output impedance or resistance. Sometimes in some text it is given resistance, in other text it is given impedance. So impedance is normally considered whenever it involve any electrical or electronic component which is dependent upon frequency. So this is R out. And the third aim is to estimate the voltage gain AV, right? So for proceeding further, we have to draw a mid-frequency small signal equivalent circuit of this main circuit, right? So this is my circuit diagram of common source RC coupled cascade amplifier. Next, we have to draw the mid frequency. Let me write it down. We have to draw the mid frequency small signal, mid frequency small signal equivalent circuit. Okay. So with the help of that, we can easily calculate the input impedance, output impedance, and the voltage gain. So now in a moment, let us start with the analysis. So to draw the mid-frequency small signal equivalent circuit, there are certain conditions which we have to follow. So what are those conditions? The first condition is that we have to we have to short circuit the connected capacitors, short circuit connected capacitors in the form of coupling and bypass capacitors. Okay, so connected capacitors will be CC1, then CC2, CC3, bypass capacitor CS1, and bypass capacitor CS2. We can have a look at it. So in the first stage, we have, CC1 is the input coupling capacitor. CC2 is coupling the first stage to the second stage. CS1 is the bypass capacitor. In the second stage, we have CC3 as output coupling capacitor, CS2 as a blocking, the bypass capacitor, right? And your source consists of internal resistance R sig. And here we have a resistive load, right? So now we have to short circuit connected capacitors CC1, CC2, CC3, CS1, and CS2. The second condition is that since we are analyzing a small signal equivalent circuit, we have to short circuit any DC independent DC sources. So short circuit DC source if they are present. Yes, DC source in the form of VDD is present. So VDD we have to short circuit, right? So over here we have VDD, right? And that we have to short circuit. And also finally, we have to replace the MOSFET by its small signal model. Okay, high frequency, small signal model of the MOSFET. So let us begin. So first of all, we will draw the small signal model of the MOSFET, right? So we will draw the gate terminal. So this is my gate terminal. Then let me just draw this. Yeah, yeah. So first of all, we will have gate terminal. So this is my gate terminal. This is my source terminal. And over here, this is my drain terminal, drain one, right? So between gate and source, we know in a MOSFET, we will have an open circuit. So we'll write over here plus minus VGS1. And what is the name of this current source? It is GM1 into VGS1. All right. And also we'll consider the RO1 over here. RO1, or sometimes it is also called as small RD. So over here we will write RO1. So this is my small signal model for MOSFET M1. Now let me leave some space and also draw the small signal model for M2 transistor. So I think this much space is enough. Now here I will draw the M2 transistor. So yeah, over here we will have a voltage dependent current source, and also we will have RO2. Okay, so this will be RO2. Then let me mark the terminal. This is gate 2, drain 2, and source 2, right? So between the gate and source, we have open circuit. So we'll write over here VGS2. Then this will be GM2 into VGS2, the name of the current source, right? And finally, let me draw it a little ahead. Let me rub this out and draw this register a little on left hand side. Yeah. So this is RO2. And this current source will be GM2 into VGS2. We are not doing anything great. We are just drawn the small signal model of both M1 and M2. Let's go back to the circuit diagram. Yeah. So we have just drawn the small signal model for M1 transistor and M2 transistor. Now let's start connecting the terminals properly. All the remaining components. So let's trace the gate 1 terminal. So from gate 1 we will have R1 register. So this terminal will be connected to the ground because VDD is sorted. And so R1 and R2 will become in parallel, right? Then we have to short circuit CC1, and in series with it, we will have RC resistance along with source. So let's do the connection for gate 1. So from gate 1, we will have, let me draw so these resistors are R1 parallel to R2, and this will be going to the ground. Then in series, we will have R6 And finally, we will also have Vs over here. So this will be Vs, this will be R sig, right? So gate 1 connections are completed now. Now let us again go back to the circuit diagram and check out for source 1 connection. So from the source 1, we have a resistor RS1, and in parallel to we'll have a capacitor CS1, right? So all the connected capacitors are considered to be a short. So a short parallel to a resistor will be a short only. So S1 will be directly, source 1 will be directly connected to the ground. So let us connect the source 1 terminal to the ground. So over here, I will connect the source 1 terminal towards the ground. Next, let us check the connections between the drain 1 and the gate 2 terminal. So let us check it out. From the drain 1, we will have a resistor RD1 going to the ground because this terminal will be connected to the ground. Then we have a direct connection between. Okay. So as I was saying, the drain 1 terminal is directly connected to the gate 2 terminal because capacitor CC2 is acting as a short circuit for this analysis. And from gate 2, we have R3. R3, this node will be connected to the ground as VDD is also grounded, and R4 also will be connected. So that means R3 and R4 will also be connected in parallel, right? So that is what's the connection between drain 1 and gate 2. So let us do that connections over here in the mid-frequency small signal model. So from drain 1, we will have over here one resistor going towards the ground, which we can, which is called as RD1. And then there is a direct connection between the drain 1 and the gate 2 terminal, right? And from the gate 2, we have two resistors which are connected in parallel. And those resistances are R3 parallel to R4. Let me rewrite it properly. That will be R3 parallel to R4. Yeah. Now let's check the connection at the source 2 and drain 2. So from the source 2, we have resistor RS2 and a capacitor CS2. Now CS2 capacitor, all the connected capacitor will be acting as a short circuit. So a short circuit in parallel with a resistor will be a short circuit itself. So source 2 will be connected towards the ground. And at the drain 2, we will have RD2. This terminal will be going to the ground, and this here will have a short circuit and will have RL. That means RL and RD2 will be connected to the ground, right? We have done this analysis before, so that's why I'm not going in that much detail, but that is what will eventually happen. So let's do the remaining connections. So over here, we have source to terminal, which will be directly connected to the ground. And from the drain terminal, we have two resistances connected in parallel. So first is RD2, and over here we'll have RL also. So here is my resistance RL, and here we have V out. Okay. So with this, we complete the mid-frequency small signal equivalent circuit. Now let me just minimize a bit so that entire circuit can be viewed together. Yeah. So this is the entire circuit, right? And over here we will have, this is my first stage. So over here till here, I have my first stage. So let us do some naming conventions. So first of all, we will rename, we will be naming this point as V in because this is Vs. So Vs and V in are not same. So this is my V in, voltage V in. Then also I will be marking, see at the output of the first stage, that is RD1, we can mark a voltage which is called as V1. Okay. So we can have a voltage V1 over here. So V1 is the output of the first stage, but input to the second stage, right? And finally, we will be calculating the voltage gain now. So the voltage gain of the first stage, we will calculate the voltage gain in this manner, right? So for voltage gain, we will have, let me write it over here. So first of all, we have to calculate, let's say, uh, first let's calculate the input resistance or input impedance. So remember, in case of your cascade amplifier, if it is a two-stage cascade amplifier, the input impedance is the input impedance of the first stage. So let's concentrate our attention on the first stage itself. So this is my first stage, right? So what will be my input impedance, right? So if I take my pen over here and mark it, let's call this as Zi and let's call this as Zin. So what's the difference between Zi and Zin? In Zin, we are considering the internal resistance also of the source, right? And Zi is the input impedance of the amplifier, right? Excluding the source. So let us calculate what is Zi. So as we have already seen the, you know, let me write first point. So Zin input impedance will be the input impedance of the first stage. Okay, in a cascaded network, input impedance of the cascade amplifier will be input impedance of the first stage. So here if you see, what is Zi, if you stand over here, what do you see on the right hand side? R1 parallel to R2, right? So R1 parallel to R2 is my Zi, because here it is an open circuit. And what will be Zin? Zin will be R sig plus Zi, right? So let us write it down now. So over here we can write Zi will be R1 parallel to R2, and finally your Zin will be equal to R sig plus Zi. Okay, so here I will write R sig plus Zi, which is R1 parallel to R2. Correct? So this is how we calculate the input resistance of a cascade amplifier. Now, second, we have to calculate the output impedance, Z out. So remember, the output impedance of a cascade amplifier is equal to the output impedance of the last stage, right? So in this case, the output impedance of the last stage means second stage. So let's go to the second stage over here and calculate the output impedance. So from here, if we mark the point from here, if we have to calculate the output impedance, what will be it? So this is my Z out. Now, what do you see over here? You will see RL, you see RD2, capital RD2, and small RO2. And then the input impedance offered by the current source will be infinite. So the Z out will be small RO2 parallel to capital RD2 parallel to RL. So let us write it down. So over here we will have Z out, which will be RO2 parallel to capital RD2 parallel to RL. So this will be the output impedance of cascaded amplifier, of the given cascaded amplifier. Fine. Now, next, we have to calculate the overall voltage gain. Now, what is my, let me just write it over here first, and then we will put it on paper. So what is the gain of the first stage? The gain of the first stage, will let us call it as AV1. That will be V1 divided by V in, correct? And what is the gain of the second stage? Second stage will be uh, V out divided by V1, right? Because V1 is the input of the second stage, right? So I can write over here AV2 will be V out upon V1, right? But what will be the overall voltage gain? Because we want overall voltage gain to be V out upon Vs, correct? So what will be V out upon Vs? So we have to write in terms of Vs. So V in upon Vs also we have to calculate, correct? So now let me write it over here officially. Third, we have to calculate the overall voltage gain AV, which is V out upon Vs, which can be written as V out upon V1 into V1 upon Vin into Vin upon Vs, right? The first over here is my second stage gain here. This is AV2. The next is AV1, the gain of the first stage. And this is due to that voltage divider over here, right? Because of the internal resistance, like this. So we have Vs over here, we have Zi over here, right? So R1 parallel to R2. So let me redraw it, and here we have V in. So let me redraw that part over here so that it will show it to you how to calculate those things. So let me draw it over here. So here we have R6. Then we have R1 parallel to R2. This is R6. Over here we have Vs, and over here we have Vn. So now by simple VDR, by voltage division rule, can we write V in terms of Vs? Yes. So V in will be R2 divided by R2, or we can call this as Zi, right? So V in will be Zi divided by R6 plus Zi into Vs. So that into Vs will come over here, and we can write V in divided by Vs will be equal to Zi divided by Zi plus R6, right? So this term is evaluated, V in upon Vs is calculated. Now we have to calculate AV2 and AV1, right? So let's start with the analysis of AV1 and AV2. Now let's look at this diagram, and first always calculate AV2, correct? So let me have some space over here. I'll use a different color. So now, what is my V out? Can anyone tell me what is the V out? V out can be written as, so these three resistances are in parallel, right? So, and this will be the current. This is the current which is flowing in this three resistance, but it is, this current is not going towards the ground. It's moving away. So we can write V out is equal to IR. So minus of minus, because the current direction is opposite. So this is current, right? Minus GM2 into VGS2. This is my current into the resistances, right? So what are the resistances over here? RO2 parallel to RD2 parallel to RL, right? So this current into this resistances. And according to the diagram, what is the VGS2? If you see, VGS2 is same as V1. VGS2 and V1 are in parallel, right? So what we can do is, next step, VGS2 is equal to V1, right? And now if I write over here, what will be V out divided by V1? It will be minus GM2 into RO2 parallel to RD2 parallel to RL, right? So this becomes my voltage gain for the second stage. This is AV2. This is the voltage gain for the second stage, right? The important one, important formula, we have to calculate the gain stage wise, right? So this is my value for AV2. Now similarly, let's calculate the value for AV1. So for AV1, we have to go over here, right? Now over here, let me use another color. Let me use orange color over here, right? Now tell me what will be V1. So V1 will be equal to these four resistances, RO2 parallel to RD1 parallel to R3 parallel to R4 into the current. This current is again going outwards. So this current will be minus GM1 into VGS1. Okay. So minus this current means the current is going outward, not towards the ground, into the resistances, which is RO1 parallel to RD1 parallel to R3 parallel to R4. So what I will do is I'll rewrite this below, But first of all, let me know what is VGS1. VGS1 isn't it parallel to V in? Yes, they are in parallel. So we'll go down and we'll rewrite these things. So we are calculating AV1, and we have written an expression that V1 is equal to minus of GM1 into VGS1. This was the current, right? Into RO1 parallel to RD1 parallel to R3 parallel to R4. I think we have just written this expression just now, as we have seen. This marked in orange color, we have written it down. That's it. Nothing great. Okay. And also your VGS1 is equal to V in, right? Now, if I divide V1 divided by V in, what I will get? Minus of GM1 into RO1 parallel to RD1 parallel to R3 parallel to R4, right? So this equation is signifying the voltage gain of the first stage. So this is my voltage gain of the first stage, right? So this voltage stage of the first stage, you multiply it with the voltage gain of the second stage over here. Where is the second stage? Yeah, this is the voltage gain of the second stage, and that itself you multiply it with V in upon Vs, which is just term over here, right? So finally, if we want to write an expression of AV total, so how can we write AV overall? So it will be AV, which is equal to AV1 expression multiplied by AV2 expression and further multiplied by Zi upon Zi plus R6. Okay, and this is the final overall voltage gain of cascade amplifier, right? RC coupled, common source, RC coupled cascade amplifier, right? If you all have any doubts, you all can ask them right now, or else we have completed our objective of calculating the voltage gain, overall voltage gain, input resistance, output resistance, and the overall voltage gain for a common source RC coupled cascade amplifier. Okay, so that's all for this session. We have completed the analysis of common source RC coupled cascade amplifier. Next time we will solve a numerical on the same circuit. Okay, so next time we'll solve a numerical on the common source RC coupled cascade amplifier. So that's all for today. Thank you for joining and have a good day.